Hello, I'm Deborah Chung. I'd like to talk to you about the marvelous design in nature. Now, a watch, for instance, needs to be designed. And design involves intricate, careful work. If you have an explosion, the consequence is disorder. It's not order. Even a birthday cake needs to be designed. Okay? And in nature, we see just marvelous design, very, very intelligent. One example is that a solid is usually denser than its liquid. So to the left is the liquid, and the right is the solid, and these atoms or molecules are more closely packed in the solid than the liquid, and that's the norm. Okay? However, there is an exception to this, and that exception pertains to H2O, the water molecule. You know, in liquid water, the water molecules are packed together, whereas in the solid ice, the water molecules are spaced apart. Okay? And as a result, the ice has lower density than water, just the opposite from the norm. As a result, ice floats on water. Also, ice floats on a lake. Even if the whole surface of the lake is frozen, underneath the ice is still liquid water. And so the fish and various kinds of crabs and shrimp, they survive, even if the lake is totally frozen on top. Okay? Now, if ice were to be denser than liquid water, then after the top has frozen, it would sink down. And the water comes up and gets frozen again, and then after getting frozen would sink down again until the whole of the lake, from top to bottom, is all frozen. And that would be terrible. All the fish would be dead. But this doesn't happen because of this one exception, that the density of ice is in fact lower than that of water. And this abnormality is because the oxygen is a little negative and the hydrogen is a little positive in the electrical charge. And because of that interaction due to the charges, you have this structure in the solid ice. And this very nice hexagonal structure gives rise to the beautiful snowflake. Okay? Okay, let's now turn to another beautiful design in nature, and that's the design of a leaf. Okay? Well, you have a plant here, and the water is absorbed by the roots, and then the water travels up through the plant and get to the leaves. But they have to get out of the leaves somehow, otherwise the leaf would be oversaturated and blow up. So water vapor actually get lost from the pores of the leaf, and that process is called transpiration. And that transpiration effectively pumps the water upward. Okay, it's very important for the water vapor to be able to get out of the leaf. Okay? So the pores on the leaf are very, very important. This is a situation where the pores are mostly closed, and you have the water vapor as well as oxygen be able to get out. But when you want the carbon dioxide to get into the leaf, then the pore needs to be really opened. So these are just valves, okay, and very, very microscopic valves. See, this very microscopic, blown up in this picture. These are microscopic valves in nature. Now, if water completely covers the surface of a leaf, then it would cover all those pores and no transpiration can take place, and the plant would suffer. However, the leaf still wants some water. So water droplets would be nice. Okay? Instead of a whole complete layer of water, they're just water droplets on the leaf. Okay? But how can water droplets be formed on the leaf? Well, that's because the leaves have a waxy coating. It's like oil and water, not wanting to mix. As a result of the waxy coating, you end up having water droplets on the leaf instead of one complete layer of water. Not only that, it'd be nice if these water droplets move rather than being stationary. Okay? And they do move because of the shape of the leaf, allowing the water droplets to simply roll down the leaf. So even the shape of the leaf has been designed. Another aspect of the leaf design relates to the veinlets, the very little pipes, microscopic pipes for the water to go through to all the area of a leaf. Okay? Again, very microscopic. And nowadays, we have a field of science known as microfluidics, meaning you have little pipes or little channels for fluid to go through, and this is for checking the blood. Okay, so you have, say, a drop of blood put into this little plate, which they call a chip. And then along with the chip, you have various gadgets for testing this blood. And so this chip acts like a little lab, and they call it lab on a chip. Very fashionable. And nowadays, they use the same concept for COVID testing. You might have done that already. I have. Okay, microfluidic channels. But the veinlets are really microfluidic channels, and they have been around for a long, long time in nature. And these are really microscopic. You know, these are bigger, and then these are very, very tiny ones. Another aspect of leaves has to do with the plant fibers. Okay? Especially if the leaf is long and thin, you have pretty strong fibers along the length of the leaf. And sisal is a kind of plant which has these long, narrow leaves, and they provide sisal fibers, which are mechanically pretty good. And one can have a factory making the sisal fiber from the sisal leaf and weaving the sisal fiber to make handbags and various gadgets. Nowadays, we have glass fibers and also carbon fibers. The carbon fibers in particular are light and strong, and so they are used for aircraft. Okay? However, these carbon fibers and glass fibers actually just follow the plant fibers, the same concept. Okay? And these natural fibers have been around for ages. So the design of a leaf is really multifaceted. It's tremendous. Another aspect of nature's design relates to the spider web. Okay? The spider in the middle, and you see the web. The silk that makes up the web is not that densely packed, pretty far apart from one strand to the other, yet the overall web is mechanically pretty sturdy. It's not easy to break it. Okay? And the spider vomits some silk material out to make these silk fibers and weave them together with the legs sticking out for the weaving. It's just like ballet. It's a pretty intelligent weaving, and the spider silk is mechanically very nice. And nowadays, architects use this design called geodesic architecture, which simply copies from the spider web. You see all these struts making up the overall architecture, and it's really like the spider web. So even from the spider web, we can see beautiful design. Not only the appearance, but the material and how it's made. Okay, another aspect of nature's design pertains to breathing. which is obviously very important to us. In breathing, we take in oxygen and we breathe out carbon dioxide. And everybody, in fact, all the animals do the same thing. In the air, there's only a limited amount of oxygen, 21%. Well, if everybody takes in the oxygen, would the air eventually get deprived of oxygen? Well, that doesn't happen because it's been designed so that the plants breathe in carbon dioxide and breathe out oxygen, the exact opposite of the animals. So it's a great balance. We don't have to worry about the oxygen in the air being less and less for us to breathe in. Now, carbon dioxide is evolved when we do barbecue, and also when we burn coal in the factories. Carbon dioxide is also evolved, and the plants are very important for sucking in the carbon dioxide, again providing the balance so that we wouldn't get pollution. Okay? And the leaves take in the carbon dioxide through these pores that we talked about. Okay? And they also give out oxygen. Okay? And that giving out of oxygen is very important for us because we need the oxygen. And so trees and plants are very important for the overall environment, providing that balance so that we have oxygen and we don't get the environment polluted with carbon dioxide. Now, fish, as well as other animals, also inhale oxygen and exhale carbon dioxide. Okay? Fish and birds in particular. Now, fish need oxygen, but fish live in water. And water contains very little oxygen dissolved in the water. A few parts per million of oxygen dissolved in the water. So that could be a difficulty for the fish. However, nature has it worked out. Fish drink much water with the mouth wide open. It just takes in lots and lots of water, even though it's part per million of oxygen in the water, but it takes in lots of water. And in inhaling, the fish open the mouth with the gill cover closed. And the gills serve to absorb the oxygen from the water. And then afterward, it has to exhale, otherwise too much water that the fish just burst. It cannot do that. So it has to exhale. And that occurs with the mouth closed and the gill cover open, and the water comes out. Okay? And here, the gills have already taken in the oxygen, so the remaining water would go out. I mentioned that ice floats on a lake so that the fish can survive even though the top of the lake is all frozen. So the design in nature is really nice for the fish, providing a means of taking in oxygen and also being able to survive in deep winter. Now, birds need much energy for flying. They go up and down, left and right, pretty fast. Okay? Because of that, they need a lot of oxygen. Okay? So how can they get a lot of oxygen? They have lungs, but on top of the lungs, they have big air sacs, which act like pumps, allowing the air to be pumped so that the lungs become very, very efficient. Now, human beings just have the lungs, but we don't have those air sacs. So our breathing is far less efficient than the birds. Okay? And not only that, birds are very maneuverable in their flying, very agile, durable, small, and also quiet. Okay. The bird can land on this wire and just sit on it very comfortably. No aircraft can do that. Okay. The birds don't need any aircraft runway up or down. They don't need batteries, and don't need any combustion engine, and they don't give pollution. Okay. This is a dragonfly, very, very tiny. See, this is one finger, see? The tip of a finger. And so this dragonfly is extremely tiny, but it has great lifting power. You know, it can lift because of these big, big wings, which are specially designed to create little whirlwinds over their top surfaces. And you know, the wing design in this case is very intelligent. Now, our aircraft can fly, but they are not as intelligent. Limited maneuverability, needing an aircraft runway. Also, it's polluting because of the engine. Also, it's noisy because of the propulsion. And also, it's large. Now, nowadays, people are trying to develop what's called air taxi, which is an electric aircraft that's parked here, and they fly from one point of a town to another point of a town very quietly. Obviously, has to be quiet because they fly around within the town, and so they cannot use a combustion engine like an aircraft, like an ordinary aircraft, because that would be too noisy. And so they use batteries. And for electric vehicles, you know, this is electric aircraft. It needs a lot more energy than electric cars. You know? So the battery requirement is huge, and that's very difficult. They don't have it developed yet. Okay? We are very far from the technology of birds. This is American Airlines Flight 587. In 2001, it fell down from the sky of New York City, killing over 200 people. And that happened partly because the plane's tail got detached. The tail of a plane can be detached because of the screws and fastener here. You know, screws, you know, that sounds like very old technology, but that was the problem. Because this fastening, as they call it, got bad, this tail got detached, and without a tail, the aircraft cannot function. Now, 2003, the space shuttle disintegrated upon re-entry. Okay? This is upon disintegration, and these 7 astronauts lost their lives. And that was because something came off, and that something was the thermal protection tile, these black squares on the surface of the space shuttle. Because of the tremendous amount of heat that the space shuttle has to endure, especially during the re-entry, it needs a lot of thermal protection, as they call it, thermal insulation. And it turned out that during the takeoff, some of these protection tiles came off. Again, a joining problem. As a result, upon returning, the space shuttle could not survive. Okay? And one would think, oh, this adhesion should be a simple technology. Well, but that was it. Now, our technology is full of mishaps. You know, it's not so reliable. Now, this is a tunnel in Boston. This tunnel goes to the airport in Boston. Okay? And this tunnel has a concrete drop ceiling. Okay? Big concrete slabs, each weighing tons. And these slabs are hung down from the top using steel, and the steel is joined to the concrete slabs. Another joining problem. And because of this joining problem, some of those concrete slabs fell down, and a woman was crushed to death in her car. Okay. So, joining problem, okay? Joining the steel to the concrete. In nature, on the other hand, joining is not such a big problem, just like our tooth. Okay? The top layers of a tooth consist of the enamel at the top and the dentin below it. Okay? It's not easy to get the enamel out of, out of the tooth. You know? It sticks very well. Okay? Now, we might have tooth filling, yeah, but it can happen. It has happened to me that after so many years, the filling comes off. Okay? And you have to refill it. You know? Again, joining problem. All right, let's look at Niagara Falls. It's very close to my home. It's durable and majestic, so powerful, so beautiful, and yet it stays looking like that century after century. Okay. However, man-made stuff is not quite as durable. This here in New Orleans in year 2005, the levee breached. As a result, the city was flooded by the water from the lake, and a lot of people died. Okay. Well, a steel reinforced concrete is supposed to be a very well-developed structural material, very widely used for the civil infrastructure. But in 2007, in Minneapolis, this bridge suddenly collapsed, and a few people died. Okay. So, oh yes, here, another incident. In Miami in 2021, this building collapsed before and after. Okay. So steel reinforced concrete seems to be not as reliable as it should have been. Why? It has to do with the steel in the concrete being corroded. You see the corrosion. And this corrosion is particularly likely if the concrete is near the water, like in Miami, you know, near the water, or that bridge, you know, near the water again. And being near the water is more likely for the steel in the concrete to get corroded. Now, without the steel, the concrete is just too weak. So the concrete has to have the steel reinforcement, even though the reinforcement faces the corrosion problem. Now, concrete itself is not very strong. That's why it needs the steel. And why is concrete itself not very strong? Well, concrete consists of stones and sand particles all bound together by using cement. And it turns out that the cementitious bonding is not a very strong kind of bonding. As a result, the overall concrete is not mechanically that strong. Okay. Now, let's look at nature. Yeah. This is a little cave with some water in the cave. This is in Greece. And the water is right next to the rocks. See, right next to it. And there's no steel in the rocks, but the rocks are perfectly fine, very durable, no degradation. That's nature. There's no steel involved in the rocks. The rocks are very strong by themselves. They don't need steel reinforcement. Another example is the water coming down the rocks as a form of waterfall. Okay? And the water touches the rocks. It actually touches, not just nearby, actually touching the rocks. And again, very durable. The rocks don't have steel, yet very durable. This is nature. Okay? Here, oh, this huge rock. This person is so tiny here. Okay? Again, no steel in the rock, and it's very sturdy. Okay? So we just have to marvel at nature. The technology is so far ahead compared to our 21st century technology. Well, another aspect relates to the eye, our human eye. We have pupil and lens in front, and then we have the retina at the back, okay? And the retina has a lot of light sensors, very, very densely packed. And so when the light shines onto the retina, the light sensors would work to allow us to be able to see. Okay? Lots and lots of very densely packed light sensors. And it's even more densely packed, more complicated than the integrated circuit that we have nowadays. So the eye is really a machine, okay, with all these components, and that machine requires design. Darwin, who put forth the principle of evolution, he said this: complex organs, such as the eye, would be difficult to explain in terms of the gradual, stepwise process outlined. He saw the loophole in his theory because a complex organ has these multiple parts. They have to be all present at the same time, all positioned relative to one another properly so that this organ can function. Okay? You cannot have just one part come in and after 1,000 years another part come in. You cannot do that. All the parts have to be together, properly positioned in order for the overall organ to function. Now, our eye is most sensitive to green color. This is the human eye response. The response is largest for the green, not so great for the red or the violet. Okay? And nature is mostly green. The nature has been designed in consideration of our eye sensitivity so that we can enjoy nature very well. Now, this is a single cell. The single cell has a lot of stuff in it, various chemicals like proteins, various signals that travel around, and also a nucleus. And inside that nucleus is DNA, which is the molecule that contains the genetic code. That is your skin color, your face texture, all the details of your about how you are in appearance as well as in your ability, all inside this genetic code, and that's all in the DNA molecule. So this is a digital information storage that's molecular, and that's in our DNA. In everybody's DNA is different. Everybody's DNA is different. Different animals, different plants also have different DNA. And so the digital information, very plentiful, was introduced to the universe at the very beginning. Now, in order for all the different human beings, all the different plants, and all the different birds and fish and so on to differ in the DNA, there has to be a lot of different versions of the molecule. So the creator is a programmer with an infinite number of algorithms. All right, so this is again a single cell showing the cell membrane. And here is the nucleus with this DNA inside. The cell membrane can contain various things to help the cell function. One of the things is a motor for creating energy. Okay? Now, the cell membrane is pretty small, so the motor has to be very tiny. The diameter is about 50 nanometer, very tiny. Not only that, the motor can rotate at a speed of 1,700 revolutions per second. Very, very high speed, so that the energy generation can be very efficient. Okay? There could be a propeller here, and so the motor allows the propeller to wiggle around. And the bacteria has this tail, which is the propeller, and the propeller can swim because of that. Okay. We have motors around, okay, but they are very big, and they rotate, but not quite as very slow compared to what I just said. Just very clumsy and far less efficient. Okay, so in spite of our 21st century science, we are nowhere near what is around in nature. All right, let's look at heartbeat. Okay, very important. How does our heart beat? Okay. This is our heart, okay? And it beats because there's a cell here which has the function of giving off a signal. And that signal is then transferred from one cell to another until the whole of the wall of the heart receives that signal, and the whole heart can then work together, say they contract and pump the blood. Okay? And in order for the signal to be transmitted from one cell to another, there are molecules that jump from one cell to the next. Okay? There's no electric current flowing. It's just the molecules moving. And now let's consider our the technology of mankind. Some people have the heartbeat not beating very well, maybe not very regularly, so they need a pacemaker. Okay? The pacemaker sends out a current, namely electrons. So the electrons flow in this wire, which gets to the tip of the heart. Okay? And one pulse of the current results in one heartbeat. Okay? And that's how the pacemaker regulates the heartbeat. It sounds like a great technology, but there is difficulty. One difficulty is because of the radio wave interfering with the electrons moving in that wire. Radio waves are all over the place nowadays, not only being emitted from cell phones and TVs and microwave ovens, but also Wi-Fi and everywhere nowadays. There's one place where radio wave is particularly strong, and that's the MRI instrument in the hospital. Okay, MRI is used to look at various organs, including the brain. Patients having a pacemaker cannot undergo MRI because their pacemaker can malfunction due to the interference of the radio wave with that wire, with the electrons flowing in that wire between the battery and the heart. And that's a big problem because the MRI is very important technique to find out what's wrong with your organs. And if you cannot go through MRI, you're kind of partly in the dark. That's a big deal. So it's a problem. Well, nowadays, they have advanced the technology a bit by using so-called leadless pacemaker, which means that the battery and the wire is all packed together in one little package. It involves a more dense kind of packaging, but still it involves a battery, still involves the wire, still involves electrons traveling the wire. So the problem of the pacemaker patient not being able to go through MRI remains. Another problem is that the pacemaker requires a battery, so that you can send a current to activate the heartbeat. And the battery life is limited. And so surgery is needed to change the battery. And you'd better change it before the battery dies. But in nature, there's no battery needed, no electric current needed, because there's this cell which provides the signal for activating the heartbeat. Okay? Well, you might say, wow, cell, why is it able to do that? Well, the cell is a very complex entity. You know, this is a single cell, lots of different stuff in it. It's capable of many, many functions. I already mentioned about that motor, right? There are many functions involved. In the signals moving around and chemicals moving around. The cell is really like a factory. Okay? And not only that, it has life. For instance, you can have a single cell dividing into two cells, and that's growth. Okay? A living thing can grow. Okay? And there's no need of a battery for that. So we are a very long way from the technology of a cell, okay? Because we are still dealing with non-living things, like that battery, that wire. Those are all non-living things. So we're still in the realm of technology based on non-living things. A robot needs a battery. We do not. And living and non-living things are hugely different. Now, you might have a reaction, A plus B becoming AB. But if A and B are non-living things, AB is going to be also non-living. AB is not going to be living. You know, the science cannot consider how a non-living thing can be converted to a living thing. That's a totally open question in science. Just science cannot explain how a living thing can be formed from a non-living thing. This is Darwin's tree, and it starts with a single cell at the bottom, and it evolves into various organisms. But at the bottom is a single cell. That's living. It's living to start with. Okay? So Darwin does not address at all how this living single cell comes into being from non-living things. He doesn't touch that at all. Okay? People have achieved a lot, but their intelligence is tiny compared to the creators. Okay, let's consider yet another aspect of nature's design. This is a very big aspect involving the planets and the solar system. The planets in the solar system move around the sun in the middle. Okay? And the four seasons come about because the Earth moves around the sun, and the north-south pole that is not vertical, that's an angle. And because of that angle, we have the four seasons. And so that angle has been fine-tuned from day one. And the speed of light, electronic charge, and all those have been fine-tuned from the very, very beginning, so that we can live on Earth comfortably. If any of these physical constants are changed a little bit, we would be in trouble. Now, Einstein understands that very well, because if any of these constants is changed a little, the distance between the sun and the Earth might be changed a little. We might be frozen, or we might burn. And Einstein himself said, God does not play dice with the universe. Brian Josephson Nobel Prize winner in physics in 1973, he said, "Intelligent design is valid science." The Bible says, "For since the creation of the world, God's invisible qualities, his eternal power and divine nature have been clearly seen, being understood from what has been made, so that men are without excuse." It is a miracle to have a baby. Okay, from the beginning to the end, it's a miracle. It's not because we are smart that we can have a baby. It's just something beyond our ability. And the Bible says, "For you created my inmost being. You knit me together in my mother's womb. I praise you because I am fearfully and wonderfully made. Your works are wonderful. I know that full well." God designed us, so we are God's intelligent property. Well, this picture shows an ape evolving to become a man. But this is actually conceptual, because the intermediates called Ape-man, these are drawn there. They are just drawn there. Now, this is a famous, so-called Ape-man, discovered in Java, Indonesia, these bones. And they are reportedly 11,000, 117,000 years old, very old. Okay, actually, the dating is very, very unreliable. Our present-day carbon-14 dating is not able to figure out this kind of very, very long age. Just cannot. But even if this dating is correct, being old doesn't mean that it's an ape-man. Being old can mean it's a man, right? All right. And a very important aspect of design is coordinated design. It's not just designing the chair, but designing the table along with the chair in a coordination. Okay? And we see coordinated design in nature abundantly. Man and woman designed in a coordinated fashion so that they can reproduce. Okay? Animals and plants are designed in a coordinated fashion so that animals take in oxygen and plants give out oxygen. The human eye and the environment are coordinatedly designed so that the human eye is sensitive to, most sensitive to green color, and the environment is mostly green. The fish and the environment also, right? The fish needing oxygen, and the breathing of the fish is designed so that the fish can get enough oxygen from the water that has very little oxygen. Also, the fish would survive underneath the ice in the lake. Also, the universal constants, like the speed of light in physics, all these are designed in a coordinated fashion. Here's a very interesting example of coordinated design involving the crocodile and the plover bird, this little bird. And this little bird has the function of cleaning the teeth of the crocodile. And the crocodile opens its mouth and lets this bird clean its teeth. Okay. Very comfortable for both parties. What a design, coordinated design. There are various aspects of design, materials, interfaces, because you have A and B and you have to join them together, for instance. The joining is very important. Also the shape, the dimensions, the functionality, the mechanical strength, the durability, the coordination, the aesthetics, the energy, and being quiet or not, and also no pollution. Okay? So all these have to be considered. We often think that scientists are very careful and objective, very intelligent and knowledgeable. Actually, it's not quite so ideal. We know Einstein and his famous equation, which means mass is energy. Okay? And we believe in magnificent, counterintuitive things. And science is just full of trust-like beliefs. Instead of deriving everything, scientists just trust a lot of things. Okay? Say mass is energy, they just take it for granted. They believe Einstein. Time slows down with gravity and acceleration. Sounds odd, but they take it. The Earth moves around the sun at a speed of 67,000 miles per hour. Well, they take it. And that's how the science world functions. Moreover, science is limited. Science cannot address how non-life is converted to life. Also, science cannot address the spiritual realm, only the physical realm. And the spiritual realm is not bound by the laws of science. And God resides in the spiritual realm. Science considers the physical realm but cannot consider the spiritual realm at all. And just no scientist, no science can consider the spiritual realm. God also designs our lives. Okay? He wants our life to have meaning and purpose. And we are all God's masterpieces. What joy it is, what fortune it is to be God's masterpieces. Thank you.